In this video, I'm going to walk through the demo assignment. So previously in the lectorial, I have done this, but at that time, I hadn't done the assignment myself. So now I've written some of the code and I want to explain that to you. So hopefully things are a little bit more clearer now. So the first thing I did is to import numpy as np, and from numpy import sine and cosine, so I don't need to type np.sine every time. And then I define a function which takes that angle and also the axis to return that rotation matrix, and I call it get rotation matrix. So I use if else, make sure the axis is just x, y, or z. Otherwise, it will throw an error saying that it's not valid. So we can actually try this out. Pi divided by 2x. Right, see, if I put k, it will throw an error. So one thing you'll notice is that I have a string here. This is called a doc string, documentation string. So the use of that is that if we call help on this, it will actually get back to you about what this is doing. So it's very helpful if you put a doc string there and call help on that if you forget what it's doing. So next is to essentially get a function to calculate the a and b, because we want to calculate at a given time what is the magnetization for x, y, z, given the t1, t2, and also the initial state. And these three equations can be formulated into the linear algebra format, so these are equivalent. And we're going to use the latter one to define the relationship. So I changed the previous function a little bit and I call it free process, and it returns a and b at the end. So it's basically the same as that rotation function. I just translate the formula into numpy code. So here R, pay attention, I use the get rotation matrix C because it's basically the same function as the R C here. So alpha here just becomes omega t. So that's why I use this to get R, and then I use matrix multiplication to get A, because that's the definition, is to multiply the two matrices. So pay attention, this is not element-wise operation as I explained in previous videos. And this will return A and B. Alright, so with that done, we can set up the initial parameters, and we know the initial status M0 is this. And then I will name one of the variable called flip angle, so that's easier to understand. And I create a times, so that's basically all the time points. And if we look at the shape, it will be 800, so there are 800 time points. And then I initiate a variable just to hold all the results. So currently it's empty. So what I want to do is calculate one state and then I put it in one state and put it in one by one. So next thing, I want to apply the flip. So the flip is just to flip it to x or y, and then I add that result to mt. And also before that, add m0. So after executing this, mt will have two values inside that. Mt will have two values inside that. So it has four because previously I haven't cleared all the existing variables because I've run this already once. So these two, one is at the initial status and the other is flipped to the xy plane. So after that, what I need to do is basically to loop through the time, so from the third onwards, and calculate what is the A and B. So here I've taken note of what's the flip time because I want to get the time difference from that. That will give you A and B, and I can calculate the status at that particular time, and then I append it to MT. So after this step, MT should be a list that has 800 results inside it. So this corresponds to each time point, and I can actually get to a specific time point and look at what's the X, Y, Z magnetization value. And then I convert everything to Numpy array and then also transpose it so that it has a similar format as the previous code. So 3 rows and 800 columns, while each column specifies a time point. And then I can calculate magnetization in the XY plane. Basically take the X component, Y component, square them and get the square root. And finally I can plot them. So that's the FID signal.